We get to the interesting case.
I've been bored all this.
This is the problem where you're willing to trade something valuable if only you had compactness.
Yeah.
So,
I think you have 20 on the test. Just think this
so suppose you have an open, now but this is not open in the sense of math, this is open in the sense of everyday living. An open rectangular box,
It's like no lid.
by which I mean a box with no lid. A lidless,
A lonely rectangle?
it's sort of like a listless box.
A listless box.
Has surface area 3 square meters. What should its dimensions be in order to have the box hold as much as possible?
Oh, optimization.
Well, of course, we're doing optimization. What
3 feet square.
should
Regular Americans.
its dimensions
We're
be
Americans.
in order to maximize the volume contained in the
I
box?
didn't have to do it during that all yesterday.
So why is it a priori not even obvious that there is a maximum? That's actually not the point.
What if you just...
Even if I made a closed box, that wouldn't mean that the math in the problem lived in a closed, bounded set.
What if you just say you can
What?
have a line
Yeah,
that
just
goes on forever?
Yeah.
It still has surface area 3.
yeah, you can
Yeah.
you can have
If you have 3
If you would
squares,
take one
yeah, you
dimension
just-
to
you just have to keep making one
infinity,
box.
I guess is what they're trying to say, but that's just like,
So are you saying if I write down this condition, that it does not create a compact set in my set of variables?
Yes.
Yeah.
So this is didn't quite make this look parallel here, but, so if you write down x, y, and z as your dimensions of your box, as usual, so let the length, width, height, respectively, of the box be x, y, and z.
but you.
What am I trying to maximize, and what do I know about x, y, and z? So what do we want to maximize? The product, x, y, z. I'm not calling it a function yet because I'm going to get rid of a variable soon. So we want to maximize the product of the length, width, and height, but we have a constraint.
That's 2x.
What's the constraint?
2xz plus 2zy plus xy equals 3.
Okay, so there's the condition that the surface area of your box is 3 square meters. So these are all measured in meters, thank you very much.
Feet.
If it were a closed box, I would just put a 2 here. It's not changing the nature of the algebra very interestingly. Why does the set of points x, y, z, all positive, satisfying this constraint equation, not give me a compact set?
Because you could take one really long.
I could take,
Yeah, when
If one dimension could go
if one
forever
yeah.
and ever, it could be
okay, so I
infinite.
can make any one of the dimensions arbitrarily large as long as I compensate by making the other ones
Really
somewhat
large.
small.
Yeah.
Yeah.
So that doesn't sound like a bounded set in R3, does it?
Right.
No.
So first thing I want to do is take this equation and get rid of one variable and then define my function on a domain in R2. But then we're going to worry about, well, maybe did that make it compact or not? So let's see. So what variable should we get rid of?
Probably z.
All right, let's get rid of z. It appears sort of symmetrically here, I like that. Right, so if I get rid of z, then everything looks symmetric in x and y. So consider then that z would be what? 3 minus xy over twice the quantity x plus y?
Yes.
So consider f mapping some domain to be specified to R, where f of xy is now x times y times z. Okay, now let's talk about the domain a little bit here. What is this domain?
Well, x and y can equal 0.
D for domain.
X and y, oh, x doesn't equal negative y?
Whoa, 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 whoa.
Yeah.
Length, width, height should not be negative numbers.
They can't be
Oh,
zero.
yeah.
X, Y.
Yeah,
X
and
and Y
y don't
both
equal
have to be
0.
zero.
Greater than 0, so that's not sounding very close.
Well, they can't,
Wait, x
the
plus
product
y.
can't equal both.
But I can't have x and y both be 0, or my function doesn't even make sense. So you're going to say, okay, let's start off with the domain saying x and y are positive, and then what has to be true?
X plus y.
Am I? Minus xy over 2 x plus y is positive.
X plus Y is greater than
Wait, why can't
So
one
x
of them
plus
be
xy is less than 3.
Right, xy has to be less than 3, because otherwise z will come out 0 or negative. Agreed?
Agreed.
So put X plus Y.
So we're going to have not liking the axes very much at the moment, and not liking x times y equals 3. So it looks like we're in some very non-compact region that's unbounded and not closed.
That's really unfortunate.
Great.
Well, this is why I suggested when we started that you might be willing to trade something important for
A letter
some
grade.
compactness.
Trade to a letter grade.
I was thinking more of a leg or an arm.
But you know,
That was not, that was in poor taste, I apologize. All right. Well, what about continuity? Well, this function's certainly continuous. Yeah. But it's definitely got a problem when I approach the origin here, because I'm dividing by 0 at the origin.
so then it becomes non-bounded again.
However, I do want to make it, so my domain offhand seems to be this. But I do want to ask you, is there a way of defining this function even if x is 0 and y isn't? Well, sure. If x is 0 and y isn't, then this isn't 0,
The top is 3.
and the numerator is 0, so it's going to be 0 on the y-axis.
Okay.
So it naturally does make sense if I want to even include the y-axis and similarly the x-axis and say the function is 0 there.
And the same along the rhythm.
But now what about here? What about the origin? Then then I really do have a 0 in the denominator. But here's an important observation. If I consider xy over x plus y, we've talked about stuff like this before. What does that do as you approach the origin? Why does it go to 0?
Because
X,
y
Y grows faster.
X, Y is like x greater than
There's small numbers.
So do you have a way of making this mathematically precise that's like stuff we did at the beginning of chapter 3, or even the end of chapter 2?
So it's Y times X over X plus Y.
Good. And what if x and y are positive? What can you tell me about this fraction?
Less top goes to 0.
No.
It can only be 1.
Oh, yeah.
It's
At
less than
most.
1, less than or equal to 1. So notice that, recall that x over x plus y is actually less than or equal to 1 whenever x and y are greater than or equal to 0, and one of them
Is,
non-zero. So what does that tell you? And similarly, you could do it the other way. So what does that tell you, in fact, about the function xy over x plus y? It's at least 0, and what's the biggest it can be? No, no.
X or Y, depending on
y.
So,
X or
so what's the biggest it can be?
maximum of X.
Minimum.
I hear max and I hear min. Anyone want to bid?
Min.
If it's less than two things, we thought about this stuff way back in chapter 2. If you're less than two things, you have to be less than the smaller. So in fact, you could define this function to be 0 with 0, and it would be continuous. So if you said f bar of xy, which is the function xy times the stuff, when x and y are positive, and 0 when x equals 0 or y equals 0, this function is continuous. Okay? So we still have problems though, even if we're closing things up. And we could close it up here and say when x is 0, or when y is 0, or when xy is 3, what's the volume going to be?
0.
0. So but it still makes perfectly good sense. So we could actually consider it on this closed set that includes the frontier, and it would still be a continuous function. But we're still up the creek, unbounded. What are we going to do? Sigh.
We can kind of like cheat, like we used to cheat with like integrals and stuff, and
You have
limits,
not acquainted me with your
and-
cheating on integrals and stuff.
and improper integrals where you kind of take a
Take a limit.
and then
But how do I make a compact set to apply my theorem here?
Could you take like a derivative and show that it's always decreasing and therefore just truncate it? Like when you go up or like across?
So what Matthias, I think, is heading toward is the intuition that since the function is continuous and since it's 0 on this yellow stuff, as you go far up here, surely the function is getting smaller and smaller, closer and closer to 0. So if you're looking for a maximum, surely you ought to be able to truncate this region and say it's going to be smaller outside that region, and let's just look for the max in a compact set. Is this reminding you of something? Uh-huh.
Yeah.
A homework problem, one that had an upside-down box in it. Okay, so what I'm going to do at this point is I'm going to say, let's not worry about compactness for the minute. Let's be an engineer. Nothing personal, Tim. And let's just solve the problem the way you would be taught to do this normally, ignoring worries about whether there is a maximum. Let's try to find it anyway. That is sort of how a regular calculus class is taught, what I taught. So let's unencumbered, I need a cucumber,
yeah.
by compactness worries. Let's find critical points. All right, so I'm going to look for critical points. So we have to do df. Oh joy. You guys thought you had it bad in homework? So what's partial respect to x?
Well,
Why does that stuff plus?
gotta be
Plus
xy.
times the derivative of all that stuff with respect, excuse me, with respect to x.
Negative
U.
So are we doing quotient rule? How are we doing this?
Quotient.
Quotient rule? So I'm supposed to square the denominator. And then I take, how does this go?
U prime main.
low d high d low.
So the bottom times the root of the top. What's that? Minus,
All that.
This is insane.
minus the top times the derivative of the bottom. So at this point, it becomes clear that we should have factored out the 1/2 to start with, right? You can take the 2's out and make that a 2. Are we done? Is that the partial respect to x?
Well, should we also put the 2 somewhere because of subdivision?
Hmm?
Yeah,
Well, okay, well, I'm not simplifying it, but are we done with the partial respect to x?
Yeah.
All right. So then we're going to have to do the partial respect to y.
But it should be somewhat.
By your homework problem,
Could do the same with switch x and
you would, it's,
Symmetrical.
so what you proved in whatever problem number it is in homework, number C, part 1,
Thing that I have.
if you have a symmetric function, the way you get the partial respect to y is you take the partial respect to x and switch x and y. That's what you showed in your homework. So if I can simplify this, I don't have to do it all over again for the y derivative. I can just take this thing and switch x and y.
Sure.
So let's simplify this first and then we'll do that. So what does this simplify to? Well, clearly I can factor out a y,
3y minus twice
and I can factor out a twice
x plus y.
x plus y squared. That way I won't have any denominators loitering around. We learned that lesson yesterday. Okay, so what do I have left in the first term? 3 minus xy times x plus y. Now I factored out a y from this, so I'm left with an x. Denominator's cool. Negative xy, positive xy. Agreed? So I'm left with negative y squared
You're playing with fire.
minus the,
You're playing with fire, trying to simplify during your expansion.
Doing too many steps at once.
Too many steps at once.
So dead.
And I'm going to say this simplifies even more. Dan can close his eyes and ears if it makes him feel better. I've got a negative 3x here, and I've got a positive 3x here.
And you have a minus xy squared.
I've got a minus xy squared,
And a minus xy
and then that, that didn't simplify, Nick, thanks a lot.
You can combine.
So I've got the 3x's canceled, so I'm left with a 3y minus x squared y minus xy squared minus xy squared. So I have minus x squared y minus 2xy squared. Are you all paying attention?
Can we take a y out of that?
There is a point, by the way, where in all this you say, gee, I wish there were an easier way of doing these problems.
Wait, can we take a y out of that?
Yeah.
We can indeed take a y out of this. Why not?
Hopefully, why not? Well done.
So y squared.
Too much.
So I'm left with 3 minus x squared minus 2xy.
And we can just mirror that.
All right, I think I'm done. I may in fact be done for. But I have, after my little speech, I know what the y partial is going to be. It's the symmetric thing where we switch x and y. So here, with no further ado, comes the y partial. It looks much more congenial than that messy x partial.
I don't think x is squared in it, is
Whoops. Anything else I did wrong?
Let x be
Okay.
No.
So now, you say to yourself,
So.
when are both 0?
When x and y
Self runs out of the room screaming.
Wait, you have to zero.
So
I know what to do.
either this stuff is 0 or this stuff is 0,
Right.
and either this stuff is 0 or this stuff is 0. Well, could this be 0
Yes.
Yes.
Y equals 0.
when y is 0? But
which is on the
okay,
frontier.
But we don't want it,
but that's not very interesting for biggest volume.
so we should just ignore it.
So you would have x and y both 0, except it's not differentiable when both x and y is 0. But clearly, we're going to ignore any points where x is 0 or y is 0 as they give 0 volume, which isn't a maximum as far as I'm concerned, or as far as you're concerned. So if neither of these is 0, then these guys both have to be 0.
So set them equal.
No, don't set them
That's
equal
what
yet.
it's getting there.
Again, so both of these have to hold. Now you can say, both these terms, as we had yesterday, have a commonality of 3 minus 2xy. So what do you infer? You infer that if these both hold, if I subtract the equations, I find out that y squared minus x squared is 0. That's not all the information, but that's part of the information. So combining these gives that x squared equals y squared.
So x.
And since people are positive, that says x is y. You might have suspected that the symmetry, every problem you've ever done in all your Calc 1 experience, if you had a symmetric situation, you had a symmetric solution, you expected squares, you expected square boxes.
Would that be x equals plus or minus y?
Our domain is positives.
Yeah.
You have nevertheless been warned by homework problem C that you can have symmetric functions and have asymmetric critical points. But it seems that any sort of reasonable physical geometric problem seeks a symmetric answer, but I don't have a theorem to that effect for you. I've asked my friends in the physics department and they scratched their head and said, yeah, seems reasonable, but none of us has come up with a meta principle here. Just think about that. Okay, so we're not done. We have x equals y,
So we plug back
but
in,
then we plug back in and we get more
We
information.
get
We'll have the same equation twice.
like y and x equals.
So we'll have 3 minus x squared minus 2x squared equals 0. In other words, x squared is 1. In other words, x is 1 and y is 1.
So
Now you know why I chose an area of, well, you don't know yet, but you'll see why that 3 is going to be.
So plug those back in.
So what do I get? F of 1, 1 is my putative maximum value. What is f of 1, 1? Where's f? There it is. 1 times 3 minus 1 over 2 times 2. Oh, that's too hard for me. 3 minute 1,
2 over 2.
2 over 2 times 2, that's a half.
It's not a big volume.
Not a very big box, is it?
Well, it's
on
meters,
centimeter
so.
point.
It's a half cubic meter, right?
Which is
pretty big.
it's pretty. That's a lot of volume actually.
Mhm.
Meter is.
A half mile, thanks.
Yeah, it's pretty big, yeah, actually. Okay, so how do I now prove beyond a shadow of a doubt that this is the solution to the problem? So we claim that the box of maximum volume does exist and has dimensions 1 meter by 1 meter by a half meter. How many of you thought it was going to come out a cube?
It would if it was.
If it was closed, if it had the lid.
Right, if the lid had been there, it would have come out of a cube, but because there's no lid, you get more bang for your buck by making it shorter and fatter on the
It's
base.
like when you put the fence against the side of the house.
Hmm?
It's like when you do the problem with the fence and you do it against the side of the house as opposed to
Having to put
yeah.
extra fencing there. Yeah, it's completely like that. Right. All right, but now, how do I prove beyond a doubt of a shadow that this is actually the global maximum on that entire domain?
Check everywhere.
No, checking frontier points won't work. I don't have a compact set
We try.
so that the maximum value theorem will guarantee me a maximum.
We kind of look at the trends on the outside.
Well, you can make, but I want to create a compact domain. So this is like the homework problem I'm having you guys do it slightly more abstractly, of course. I want to pick a compact domain. Say, on this compact set, the maximum value theorem guarantees me a max. And then I know, moreover, that outside that compact domain, the function is much smaller than 1/2. So the strategy here is choose a compact set contained in my domain D and containing my critical point, of course. Outside of which we can guarantee that f is definitely smaller than the value it is at 1,1, namely a half. So then how does the logic work? So let's call this compact set S, so that it looks like our theorem. So the maximum value theorem guarantees me that somewhere in S, there's a maximum point. Well, we have the point we believe it is. Could it be any other point in this compact set? No. It can't be on the frontier. Why?
Because it's zero.
The function's 0 there. So it has to be an interior point. And what if we have a maximum at an interior point? What do we know has to happen there? Has to be a critical point. We only have one. Right? We have only the 1.11. So that has to be the maximum in my compact set.
Wait.
So the reasoning here is, and I'll write it on the board so we're not cramped. The reasoning is we are guaranteed by the maximum value theorem the maximum value theorem guarantees a maximum on the set S. We've reasoned that it cannot be at a frontier point, which cannot occur at a frontier point. reason f is 0 on the frontier. But by the way, now you see why I wanted to make the comment about how this f bar function really is continuous even when we put in the axes and the rest of the frontier, because then I'm really applying the theorem to f bar, which is continuous on a compact set. So, mean value theorem applied to f bar. Or you could choose your compact set to avoid the axes entirely and have it be some set that looked like this. That might happen to you in some homework, hypothetically speaking, next week. Hypothetically speaking. All right, so all we need to do then, therefore it must occur at our unique interior critical point. Okay, so all I have to do now is successfully manufacture the compact set
Yes.
so that f is small outside of it. Any ideas on how to manufacture?
I feel like we're in the wrong department for manufacturing.
As x approaches infinity, then you know that y function is 0.
No.
Well, yeah, so I'm actually trying to do a quantitative estimate here.
Okay.
I'm going to actually try to make an actual compact set with numbers in it.
That's not fun.
That's a
I want to use, whoops, I want to use this observation.
thought you would.
This tells me that if I make x small enough, if x is less than, say, a half, so everywhere in this to the left of x equals a half, so that would be in here and all the way up there, what's the biggest the function can be? If this term then is less than a half. So f of xy is xy over x plus y times 3 minus xy over 2. Agreed? So if x is less than a half, this term is less than a half. And what's this term? What's the biggest this could possibly be?
3 halves.
3 halves. Right, because xy could be getting very close to 0.
Mm-hmm.
So this is for sure, though, less than 3 halves. Now, last time I checked, that number isn't less than f of 1, 1. Darn. What do you want to do?
Square it.
Go further.
Actually, you might have to cube it.
Okay. What else does someone else want to do?
Quarter.
That is squaring it.
Just make the limit to 1/2, make it like excess be less than 1/5.
1/5.
Or something.
1/3.
That's 1/3.
Okay, well,
Oh yeah, 1/3 would do it.
Oh.
If you put in a third, you have 1/3 here times 3 halves.
Which is less than
No, it's exactly
Yeah.
equal to 1/2.
well, yeah.
But because x is less than a third,
Can't ever be.
the function will be less than a half. So define your compact set to force x and or y to be less than a third outside of your compact set. How do we do that? So define S by taking our domain and making it so that outside of my compact set, either x or y or both are less than a third. How should I define the compact set then? So I want to leave out the stuff way out here, but in fact I could leave out all of it, right? I could leave out all of this, and I'd be fine, right?
Yeah.
So what would my compact set be? It would be go to where this intersects
It's about 9.
and do this closed and bounded set, right? So intersect with x and y both greater than or equal to 1/3. Agreed?
Agreed.
So if I'm outside this region, this estimate, similarly for y, shows the function is smaller out there. Well, so in other words, I have a little bit of redundancy in my redundancy here. I want x, y, both at least a third, and their product less than or equal to 3.
Which we
And I'll let you be pedantic and check that that is closed. Well, that's easy. And bounded, well, that's also easy, because the farthest away you can be is those points. You can check that.
which is 1/3 of 9.
So there's your compact set.
Yes.
So how do you finish the proof? I sort of said it in words.
We know that.
So we know that
There would be
One
a-
half.
for all x in my compact set, f of x is at most
One half.
f of 1, 1, which is a half.
And then for all x outside of S, it's less than all x inside.
We also know that for all x outside of S, f of x is strictly less than a half. So what do we know?
The
That that's-
Half the maximum value everywhere, right? i.e. f of x is less than or equal to a half for all x in my entire domain, so 1/2 is the maximum volume, and we've done it.
Yeah, you're done.
Okay?
Yay.
So your problem number, whatever it is, letter whatever it is, D, is a general argument like this without a particular computed function. But it's convenient to know that you have adaptations of the maximum value theorem in certain non-compact settings. Okay, so I'm going to take just a couple minutes to say where we're headed. What comes next? Given a critical point, can we decide if it is a local max, a local min, what else could it be?
Saddle point.
Or a saddle point? Is that it? Does it have to be one of those?
Yes. Guess you're gonna spring something new on us.
Well, I'm asking you, am I springing or am I not?
No.
What was the definition of saddle point?
For every taking all.
We didn't say it the way Sammy just, we said a saddle point was described by saying that
Every ball.
every ball around the point has points both where the function is bigger and where the function is smaller.
Oh, right.
That seems to mean, i.e., it's everything except a local max or a local min. So it has to be one of these three kinds of things.
Perfect.
Any idea how you would look at a random function and decide, is it locally looking like this, or like this,
Take the
or
second
like this? What ought to be a way to,
The second derivative.
so how did you do this for single variable calculus? You looked at the second derivative, and we might want to have something analogous for multivariable that would make us understand, of course, these, I already showed you that pictures other than these can happen. So where we're headed is something like a Taylor polynomial. You didn't learn it this way in single variable calculus because you learned Taylor polynomials later. But what in fact you were doing with a Taylor polynomial, affectionately known as TP, is saying if you have a function that's twice differentiable and you want to look at a point A and nearby, so you take a small h, you could expand in a Taylor polynomial centered at A. And you may, I hope, recall that you had something that went like this. The Taylor polynomial would have had an A there, but if you don't want an error term, then there's, for some C, between A and A plus H.
So is that like Lagrange error bound stuff?
That, yes, that's the error formula for Taylor's theorem, right? Lagrange formula of the remainder. Well, at a critical point, this is 0. So what is happening near the point A is completely determined by the sign of the second derivative, near the point A. So we'll see that if you have continuous second derivatives, in fact, you can do the second derivative A, and that's going to tell you what's going on nearby. So if that's positive, that means that the function has to be looking like it gets bigger near A. If it's negative, the function has to be getting smaller near A. And if it's 0,
It doesn't know.
you don't know what's going on. Question mark.
Is that a saddle or we like actually don't?
It could be an inflection point, but also could be a very flat max or min too. Think of an x to the 4th curve.
Yeah.
Then the second derivative vanishes. It's still a local min, but you wouldn't know it just from the second derivative. You'd have to do higher order derivatives. So what I'm going to do tomorrow is start talking about quadratics, quadratic functions, and how you understand whether they're local maxes, local mins, or saddle points. And then by the end of the week, I will show you what the analog of the Taylor's theorem is for the calculus to tie into the quadratic stuff. Okay, that's what we'll do next.
Brought to you by